Compliant mechanisms have been widely used in aerospace, invasive surgery, adaptive gripper design, precision positioning and our daily applications. Compliant mechanism utilizes elastic parts to achieve force and motion transmission like this basic parallel mechanism. The drawback of this mechanism is that it generates parasitic motion which degrades the motion accuracy. Diminishing the parasitic motion becomes a key point to ensure a precise motion. An effective way to mitigate the parasitic motion is to add a compensation module. Two basic parallel mechanisms are connected in serial where the parasitic translation is absorbed by each other. Eight of these double parallel mechanisms constitute a compliant parallel positioner, which is previously investigated by ETA in 2003. It can achieve 2 decoupled degree of freedom with large ranges of motion and small parasitic error motions. But it still can be improved. In this animation, the motion stage moves in X direction. By connecting the stiffness center of the activated double parallel mechanisms, we can find that they are in rotation symmetry. Same as the situation when the positioner activated in the Y direction. Rotationally symmetric design makes it very compact. However, the parasitic rotation is not well constrained. When it is fully actuated, the stage rotation will occur which degrades the accuracy of the motion stage and put challenges to the actuation. To overcome this issue, we come up a simple solution. Layer 2 is the 180 degrees flipped version of Layer 1. The stiffness center of both layouts is rotationally symmetric but in opposite direction. Layer 1 and Layer 2 produce a pair of opposite stage rotation angles under a single axis actuation. Seizing this characteristic, the stage rotation of the composed two-layer design should be compensated, resulting in a zero rotation under a single axis actuation. Now the composed design is mirror-symmetric. Let's take a close look at how it works. The motion stage is moving in X direction. By connecting the stiffness center of the activated double parallel mechanism, we can notice it is mirror-symmetric about the center line. Same as the situation when it is activated in the Y direction. The parasitic motion is greatly minimized by the mirror-symmetric configuration without increasing footprint. A two-layer positioner is conceptually studied based on its rigid body model. The rigid motion stages are represented by the solid line and the double parallel mechanisms are represented by the short parallel lines. To accurately model the characteristics of the proposed two-layer positioner, the free body diagram modeling method combined with the beam-constrained model was used. By solving the constitutive equations, geometry compatibility, force equilibrium, the closed-form solution is obtained, which mainly includes the stage displacement and rotation. The captured analytical and FE results including stiffness, lost motion, actuator isolation, motion stage rotation and end stage rotation are compared with each other and it is showing a good correlation. Compared to the rotationally symmetrical design, the proposed two-layer design shows that actuator isolation, input stage parasitic rotation and motion stage parasitic rotation are significantly reduced, and that the out-of-plane stiffness is significantly increased. Each layer can be manufactured using CNC machining or electric discharge machining from a piece of aluminium plate. The overlapping relationship between the bottom layer and the top layer is secured by the screws. The composition of this positioner is very simple. Two identical mechanisms, gasket and screws. This is the manually actuated prototype moving in X direction. Motion stage moving in Y direction. Two-axis actuation. This XY compliant positioner is expected to be used for medical industry, laser micromachining, optics and photonics setups and semiconductor metrology where high precision is required, given that it has large motion range within a compact structure and high precise motion.